Question 2. A group of students investigating how the thickness of plastic rod affects the maximum force with which the rod can be pulled without breaking. 2 students discussed in the model pulling this rod, trying to make it break. Typical experiment. 2 students are discussing models to represent how the maximum force depends on the rod thickness. The student A claims that the force is directly proportional to the radius of the rod, and another student claims that the maximum force is directly proportional to the cross-sectional area of the rod. The area of the base of the cylinder graded in the gray color in the figure above. The students have collection of many rods of the same material. The rods all have the same length, but come in the range of 6 different thicknesses. Design an experiment procedure to determine which student model, if either, correctly represent how the maximum force depends on the rod thickness. In the table below, list the quantities that will be measured in your experiment. Define a symbol to represent each quantity, and also list the equipment that you would be used to measure each quantity. This kind of question, experimental problem, is a more difficult one to get a 5. So if you cannot do it, you can skip it. Only aim for the grade 4, huh?
Yes.
Just try your best first before quitting. Designing experiment procedure, you do not need to fill in every row. Okay. You may add the additional row. Quantity to be measured. The first thing is definitely the force required to pull the rod out. The force maximum. And to measure, you don't need to apply the force on both ends of this rod. You just need to fix one end to a stand somewhere firm to avoid falling, a wall or something. One end fixed, and use a force scale. There are different types of force scale. Some are very simple, like this thing, or some are like a digital sensor. You pull okay, this is the thing to measure the weight, not the force scale I'm talking about. Okay, like this thing. It has the sensor inside and the digital string to show how much force you pull out. Okay, so you need a force scale, a simple tool like this thing. Of course, there are some bigger thing with a greater range of measurement, could be up to 1000 Newton, for example. Let me see if I can find that 1000 Newton force scale. This is only up to 20 Newtons. Let's see, up to how many? Here, 1000 Newton, huh? Meaning about 100 kilogram. You can hang an object of 100 kilogram below this thing without breaking it. Okay.
Yes.
Yeah, you need a force scale to measure the force, or a force scale like this. Yeah, with a normal analog string, not a digital string, not a sensor, just analog. Okay, so a force scale to measure the force, the simple quantity. Oh, need to mention the word here. The maximum force. The symbol is F max. The equipment is force scale. The second thing we need to measure is the radius, or we can measure the diameter, because it's difficult to measure directly the radius, huh? Diameter, diameter of the rod, and the letter is D. We can measure that with what's the name of the thing? I forgot the name.
Ruler. Ruler.
A caliber. It is different from ruler because the ruler is not accurate enough. Caliber. Yeah, it's called a sliding caliber, huh? And you put the object you want to measure the diameter in between this thing like this. Yes. Let me open this image on the here. And the reading the diameter of this object. Firstly, you need the value 10 here. It means 10. Wait, the unit is inch, huh? 1 over, wait, the big thing is here, inch, doesn't matter. This is 10 millimeter, which means 1 centimeter. And then it is a little bit greater than 10 millimeter. And the next step, we need to find the two bars which are on the same line, like this bar. Okay,
Yes.
the bar on the top here and the bar on the glider, the movement part here. Here they are almost the same, but here's like better. And it is 10 times 0.05 millimeter more. 10 times 0.05 means 0.5, and you add that 0.5 to the value 10 here. So it means that the diameter of this object is 10.5 millimeter. Okay.
Yes.
Let's visit the tool. I will send you the link to how to use this caliber. How to use a caliber. This is a very important tool in measurement and physics. Caliber. And it is very popular in all the laboratory in schools. I think your school laboratory has something like this. How to use a vernier caliber and digital. We just need to use, okay, here. This is a very useful website, WikiHow. It contains like answer to every how questions, how to get a girlfriend, for example. Okay. So that is 10.5 millimeter, and this tool is a lot more accurate than a normal ruler, okay, caliber, to measure the diameter.
Yes.
And from the diameter, you can repeat the measurement of the diameter when rotating this object at different angles to ensure that the diameter is measured accurately, taking the average value, and also ensure that this is a circle, not a shape, not a symmetrical shape. Okay.
Yes.
You can rotate this object, the rod, measure diameter at different positions. That is the two things we need to measure, because from that diameter we can calculate the cross-sectional area, because we cannot measure the area directly. No way to do it directly. There actually a way using camera and some software to do the integration, but not for this level. So only those two things. Looking for the scoring guideline to check it here. Question 2 here. Measuring the radius or diameter with a different radius using a profit tool, which is a caliber. Measuring the force using profit tool, which is a force scale, a plausible practical way to directly determine the maximum force. Okay. Practical way to measure the force for given rod. Attempting to reduce experiment uncertainty in experiments that involve breaking the rods. Measure the diameter d of each rod with a ruler. They just use a ruler. That is a very silly way. Yeah, the ruler is much worse than a caliper.
Yes.
Students should pull on the rod with the force prop. Force prop is simply just another word for the force scale. Okay, until rod breaks. Record the force maximum just before breaking. Just before breaking, you need to increase the force slowly and slowly. But how do you increase that? Okay, here the way. You attach the force scale on a stand, a ceiling above. Make sure that it is so strong and firm. Okay, and this is the force scale. Okay, and then you hang the rod to this force scale. Okay, and on the other side, with a hanger, of course, you can hang different object, different weight to it, like 1 kilogram, and then increase to 1.5 kilogram, 2 kilogram, 3 kilogram, etc. Meaning you need to add different weights into it to increase the force gradually until the force is maximum and makes the rod breaks. Okay.
Yes.
So you need a bunch of different weights. like from 1 kilogram, then you increase to 1.1 kilogram, 1.2, 1.3, etc. slowly. Because if you suddenly increase from 1 kilogram to 5 kilogram, it will immediately break, and you don't know exactly which force is the minimum force required to break the rod. Okay.
Yes.
Okay, describe that. Can you please try doing that from the example here, making it more specific? Write somewhere or type in the step here, the step.
Yes.
Just try that, huh? I will help you fix that later. Measure diameter with a ruler. Pull the rod with force prop until the rod breaks. Record the maximum force. Repeat the trial several times to reduce the error. So you see that the example, the response is pretty short, not very long, huh? 12 points.
Yes.
Not very long, yeah. And it is to reduce the time. We should spend about 30 minutes to complete a question. Wait, the total time is 90 minutes, right? For 5 questions.
Yes.
90 minutes, 90 divided 5. So it should be about 18 minutes for each question. Okay, the procedure. Measure the diameter of the rod with a caliper. Rotate the rod at different positions or angles and repeat the measurement and take the average value of the diameter. Okay, repeat the measurements to reduce the random error and ensure the circular shape of the rod. Okay, that is the first step. Okay, the second step, hang the rod at below a force scale, force prop, which is fixed to a firm stand. And you can involve a diagram like this thing, okay? Fixed to a firm stand. Yes. On its top. Then hang an object, a weight, on the lower end of the rod, such as 0.5 kilogram. Before away lower end before it breaks, before the rod breaks. Gradually add more weight to the rod, more weight to the hanger, more weight to the hanger below the rod. Record the values of the hang weights, okay, until the rod starts breaking. Record the maximum force that the rod withstand. Okay, meaning the minimum force required to break it.
Yes.
Repeat all the steps above for other rods with other diameters. And repeat the experiment with identical rod if you have, but they do not mention that, huh? They didn't just mention that we have different rods with different diameters.
Yes.
Records the maximum forces for each rod. Okay, that's it. See the procedure. What's the next questions? Describe the overall procedure used to refer to the table. We've just done that, huh? Now moving on to question B.
Yes.
Now question B. For the rod of radius R0, it is determined that Fmax is F0 and indicated by the dot on the grid below. On the grid, draw and label the graphs corresponding to the two students' models of dependence of the maximum force on the rod radius. Clearly label the graph A and B for the two students corresponding to the profit model. Okay, this question is not very difficult, pretty simple actually. The student A claimed that the force is proportional to the diameter or radius, so it is supposed to be a straight line according to this student. Okay.
Yes.
So it is assumed to be the dot like this for the student A. For student A, label each graph A or B. You should not use the linear line, just use the point. I use the linear line to help seeing the data more beautifully. So twice the radius, twice the force, 3 times the radius, 3 times the force, 4 times the radius, 4 times the force, and so on. Okay, this is for the student A.
Yes.
Draw label the graphs. Yeah, okay, the graph. So it should be a linear straight line like this. For the student B, claiming that it is proportional to the cross-sectional area, and the area is pi times r squared, and therefore 2 times r, 4 times the force, huh? 4 times the force here. Let me use another color for the student B. Okay, 3 times the radius, 9 times the force, 9 times is here. So for the student B, it's going to be a parabola. Okay, not very accurate, but almost parabola like that.
Yes.
Here, and the first part of the parabola is below. This is wrong drawing. Below the green graph for the student A. Initially, it increased at a slower rate, but okay, at one is the interception, because at one radius, it is the same, huh? It's
Yes.
very important, this point. Okay, intersection point. Okay. Intersection point. The table below shows the result measurement taken by another group student for the rods of different thicknesses. On the grid, plot the data point let stay in a label axis, including either a straight line or curve to best represent the data. Okay. You see, the most difficult part is describing the procedure. Other parts are simple. Like this one, huh? I believe you can do it yourself. Here, the graph, huh? Please do it yourself. Draw the graph, the curve, basic line.
Yes.
Please do that and take a photo and send me.
Yes.
Okay. Straight line curve path representing the data. What's the next question? Which student model is more precise, closely represented by the evidence shown in the graph you drew in the posse? We can clearly see which student is correct, right?
Yes.
That is the student B saying that it is proportional to the area, the cross-sectional area. Listen more closely. Explain your reasoning. The student B modeled is more accurately represented or supported by the experimental result, data, and graph. Because the best fit curve is a quadratic graph showing the relationship between the maximum force and the square of the radius. It is proportional to the cross-sectional area. Okay.
Yes.
Done. Comparing with the answer, example response here. In the graph, the f max seems to be proportional to r squared, so that if we grab f max on the vertical axis and r squared on the horizontal axis, it should show a linear graph. Okay, I think this explanation is still acceptable. In other words, if a graph of the maximum force f max versus r squared is plotted, it is a linear graph. Okay, it is linear. It is linear. Done. Question 2.